Hi, I'm Shan Nawaz. We begin this lecture with the following corollary. If an abelian group G, if an abelian group G is an internal axiom, is an internal axiom that is G is called S1 direction through direction Sn, where these SIs are subgroups of G, then external axiom of these SIs is same as, is isomorphic to the internal axiom. This result omits the adjectives external and internal. So these two things are isomorphic via the map. These little s1, s2, so on, s, and this n tuple goes to s1 plus so on plus sn, and conversely, so this was first item, now this is second item. Conversely, the external direction is an internal direction. The external direction is an internal direction. That is S1 cross so on cross Sn is same as S1 prime direction so on direction Sn prime, where these SIs, Si prime is where Si prime is the set of all n tuples which is 0 at every component except at the ith component, and where at ith component this value is little si. This si is in big Si. This is true for all I. Now let us prove this result. So define a map say f from, we have to show the external axiom is isomorphic to internal axiom, so we define a map from external axiom of these SIs to internal axiom. By f of this n tuple, it is equal to s1 plus so on plus Sn. Clearly this is a well-defined map because this n tuple cannot have two images in the codomain, because of this uniqueness hypothesis. And now this set over here being the internal, being the direct sum of these SIs, this expression is unique. So this is a well-defined map. F is clearly, F is a homomorphism. F is a homomorphism. For if we take two elements, say for if, let us consider two elements S1 through Sn and T1 through Tn. So these are two elements in S1 cross so on cross S, and then f of S1 through Sn plus T1 through Tn. So this is same as f of S1 so this is same as f of S1 plus T1, because when we add these two n tuples component wise we get S1 plus T1 through Sn plus Tn. Now by definition of f, this is same as S1 plus T1 plus so on plus Sn plus Tn. Now G being abelian, we can write this as S1 plus so on plus Sn plus T1 plus so on plus Tn. Now this is same as f of S1 through Sn plus f of is like this, f of T1 through Tn. So f is a homomorphism. So here it is like this. So we claim that f is so we have proved that f is a homomorphism. Now to prove f is a isomorphism, it remains to show that f is bijective. Now f is clearly bijective because f is invertible. F is isomorphism since f is invertible with its inverse. So let us define f inverse from direct sum Sn to S1 cross Sn as, so an expression here, because each sum here is unique. So this S1 plus so on plus Sn, it goes to S1 through Sn. So this is the inverse of f, I mean the left inverse as well as the right inverse. So this means f is invertible and hence bijective. Now if f is bijective, then f is an isomorphism. So we are done in this case. Hence the external direct sum is isomorphic to the internal direct sum. Now to prove second, note that Si prime, which contains the elements of the form n tuples, which is 0 everywhere except at ith component, where this little si is in big Si. This is subset, sorry, this is a subset of S1 cross so on Sn. Indeed, this is a subgroup. So one can see that indeed Si prime is isomorphic to Si. Now if this is isomorphic, so we have to exhibit the isomorphism via the isomorphism, which takes the element of Si to this little Si. This is element of Si prime, this is element of Si. So one can prove that this map, which takes element of this form to this element, so one can prove that this is a bijective homomorphism. So this is an so these two groups are isomorphic. Now also S1 cross Sn, this is equal to S1 prime plus S2 prime plus so on plus Sn prime, because for any element since for this is for any element, say S1 through Sn in S1 cross so on cross Sn, can be expressed as so this S1 through Sn, this can be expressed as an element of S1 prime. So this is S1 0 0 0 0 plus an element of S2, that is 0 plus S2 0 0 0 0 plus so on plus an element of Sn. So this is 0 so on 0 so on Sn. So now it remains to prove that this is direct sum. I mean, this expression is unique. So it is not also Si prime intersection S1 prime plus so on plus si, this is capital Si, Si prime cap plus so on plus Sn. So this is singleton. This contains only 0 0 0 0. This is, one can prove this easily, because if one takes an element x in Si prime, so let us prove this thing here. For if x belongs to Si prime intersection S1, so this is Si plus so on plus Si prime plus so on plus Sn. This means that this x belongs to Si prime and x belongs to S1 prime plus so on plus Si prime plus so on plus Sn. So this cap here, Si prime cap, this is Sn prime. So if x is in Si prime, so x will be of the form, so this will imply, this thing implies x is of the form 0 so on Si so on 0. Now this will imply it is equal to S1 S2 so on Si minus 1 0 Si plus 1 so on Sn. So x has this form and x has this form, so these two components here are equal. Now on comparing these two, we get Si equal to 0 for all I, that is x is equal to 0 0 so on 0 in this case. Hence we are done. Now let us prove the another corollary. Let G be the abelian group generated by the elements of the form y1 through y n. Then if I take a linear combination here, that is sigma mi yi to be equal to 0 in G, so this is 0 in G implies mi yi is 0 for all G, for all I. So this is, if this is 0, this implies this is 0. This is true if and only if G is direct sum of these subgroups y1 direct sum through yn. Now first of all, to write G as the abelian group generated by the elements y1 y2 so on yn, it means that each G in G can be expressed as the integral combination of these yi's, that is, it can be expressed as m1 y1 plus so on plus mn yn, where these mi's are integers for all I. So this is the notation here. So this means this thing. Now let us begin to prove it. Now first of all, we suppose this combination equal to 0 implies my is 0. Then we prove that G is direct sum of these things. Then conversely, we take G to be the direct sum of these subgroups, and then we prove this combination equal to 0 implies this is 0. Suppose sigma I MIYI equal to 0 implies MIY is 0 for all I. So if G is generated by y1 through y1, then indeed G is, so if it is generated by y1 y2 yn, so we can write it as G is y1 plus so on plus yn. So we are halfway done. Now it remains to prove that each element can be uniquely expressed as sum of element from yi, or in other words, let G belongs to yi intersection y1 plus so on plus, so we have to omit yi here, so this means this is omitted, this term is not in the sum, plus so on plus yn. So if G is in yi, now G belongs to yi implies G is equal to some integral coefficient times yi, where mi belongs to z and G belongs to this sum here y1 plus so on plus yi, so this is omitted, plus so on plus yn. This will imply that G is equal m1 y1 plus so on plus mi minus 1 yi minus 1 plus mi plus 1 yi plus 1 plus so on plus mn yn. Now since these two combinations are equal, that is, this G is miy, this G is this thing, this implies miyi is same as this sum over here, m1 y1 plus so on plus mi minus 1 yi minus 1 plus mi plus 1 yi plus 1 plus so on plus mn yn. Or This means if I take to the right hand side, we get sigma j naught equal to I mi mj yj minus mi yi is equal to 0. Now this is 0, so by hypothesis this means, now if the sum is 0, this means mi is 0 for all I. So this is 0 implies, so this implies by hypothesis, this implies mi yi is 0 for all I. So this is by hypothesis. So if this is true, this means that this g is 0. Therefore g is 0. Hence, so we have first proved that g is the sum of these subgroups, and then we have proved this intersection is just singleton and contains only 0. So that means g is direct sum of these yi's. Now conversely, let g be the direct sum of these yi's. We need to prove that sigma mi equals 0. This implies mi yi is 0 for all I. So let sigma sum over I mi y is 0. So that means that is m1 plus m1 y1 plus so on plus mn yn is 0. So 0 has this expression over here. Also 0 plus so on plus 0 is also equal to 0. Since each element in this expression sum has a unique expression, so these two expressions must be equal. So by uniqueness hypothesis, we have m1 y1 is 0, m2 y2 is 0, that is mi y is 0 for all I. This is pretty much of it.